Hello guys, in this lecture we are going to see the types of polarization. Firstly, the mechanism of polarization. In dielectric materials all electrons are bound and the only motion possible in the presence of an electric field is a minor displacement of positive and negative charge in the opposite direction. The displacement is usually small compared to atomic dimensions. A dielectric in which this charge displacement takes place is said to be polarized, and its molecules are said to possess induced dipole moments. These dipoles produce their own field, which adds to that of external field. Let's see the different types of polarization. There are four types of polarization. First is electronic or induced polarization. Second, Ionic polarization. Third, Oriental polarization. And fourth, interfacial or space charge polarization. First, we will see electronic polarization. This type of polarization has to explain, or we will explain with the help of rare gases atoms, in which it is assumed that interaction among the atom is negligible. This is because the distance between the molecules is large enough and any neighbor reactions can be eliminated. A simple model of an atom on which to base the calculations of electronic polarization is that of an atom having a positive nucleus of charge, which indicating with a Z in the suffix E, Ze. Z is the atomic number of atom and E is the Z into E, that actually, and Z indicates the atomic number of the atom and E is the charge of the electron, which is surrounded by a spherical negative cloud of charge having a magnitude minus Z into E. Let's see here the figure shown with the circular part with the reference of the figure A. Here centrally the positive nuclear charge Ze is placed at the center of this circle, and the circular spherical part is considered as a negative charge, that is minus Ze. And it is assumed that the charge cloud is of uniform density and of radius capital R, which is shown here. With no external field, the nucleus is the center of this sphere of charge. Under the influence of the electric field, that is capital E, the nucleus and electron cloud shift with respect to one another by a distance x. We can consider here figure B, in which shows the centrally placed positive charge plus Ze is moved or displaced from their original position with the distance x, which is showing here with plus Ze. Under equilibrium condition, the positive charge remains at a distance x from the center due to two forces. One is of the Coulombic attraction between the charges, and other is force on the nucleus due to electric field capital E, and it is equal to ZE into capital E, which is showing is the ZE into capital capital E. The charge enclosed on the charge enclosed in the sphere of radius x can be calculated as is equal to charge enclosed in the sphere at the distance x or radius x, that is minus ze upon 4 pi r cube into 4 by 3 pi x cube, and we will get that is equal to minus z e into x cube. Obviously 4 by 3 into pi and 4 by 3 into pi will be cancelled and remain it is x cube by r cube. This one. The force of attraction, the magnitude of force of attraction will appear there due to the opposite charges, means minus ZE and plus ZE having a force of attraction. The amount of the Coulomb attraction between the this charge treated concentrated at a point and nucleus will be, that force will be the F is equals to, here F is equals to minus ZE into x cube upon r cube. This is nothing but the charge enclosed in the sphere at radius x, this into ZE. This is a negative charge, this is with negative charge into the positive charge. As we are Coulomb law, we are utilizing q1 into q2, that is positive charge, and this is negative charge, divided by 4 pi epsilon into the distance between them. So it is nothing but 4 pi epsilon into x square of the distance between them, simply. So by calculating this, we will get minus ZE square into x divided by 4 pi epsilon 0 into r cube. The total force on the nucleus must be 0 in the equilibrium. So we obtain that as equating the two forces Z into E into capital E. This is a force due to the electric field, and this is the force due to Coulomb law, as per the Coulomb law. So by equating this, we can get that x is equals to, value of the x is equals to 4 pi epsilon 0 r cube divided by ZE into capital E. The dipole moment induced by the field can be calculated or will be given as, this IND indicates the induced dipole moment. It is mentioned as a IND. P into PIND, that is dipole moment induced, is equals to Z into E into X. And we have the value of X. By putting the value of X, the dipole moment induced will appear as 4 pi epsilon 0 into r cube into capital E. This term 4 pi epsilon 0 and r, 4 pi epsilon 0 is a part of the constant, and r cube is the radius of that sphere. It is also a constant. So it is can be indicated with the alpha E. This dipole is induced by the electric field and never existed in the absence of field. The induced dipole moment is proportional to the field strength and the proportionality factor alpha E, which is called as electronic polarizability. Electronic polarizability. Note that alpha E is proportional to R cube, that is capital R raised to 3. That is, you can say the alpha is proportional to the volume of electron cloud. If a gas has capital N such atom per meter cube subjected to the homogeneous field capital E, then the electronic polarization, that is dipole moment per unit volume, is Pe is equals to N into alpha E into capital E. And also we know that the value of dipole moment can also be represented with P is equals to epsilon 0 epsilon r minus 1 into capital E. By comparing these two equations, we will get that here the epsilon 0 into epsilon r minus 1 is equals to N into alpha E. So from this equation we can calculate the value of epsilon r. This relation gives the measurable epsilon r and atomic constant alpha E. From this above equation we will get the epsilon r is equals to 1 plus 4 pi n into r cube. This is for rare gas. Because the electronic structure of an atom is relatively temperature independent, the variation of alpha E with the temperature is expected to be 0. Experiments agree that this is true. The assumption on which the calculation is based that the spherical charge cloud surrounding the nucleus has a uniform charge density is not in accord with the quantum picture of the atom. This is whole about the electronic polarization. Let's see the ionic polarization. In an ionic bond, when two different atoms join together, then there is a transfer of electrons from one atom to another. Let us consider a typical ionic compound, that is sodium chloride, NaCl. Sodium chloride, NaCl. Sodium has 11 electrons around the nucleus and chlorine has 17 electrons around its nucleus. In the sodium chloride bond, there is a transfer of an electron from sodium ion atom to negatively charged chlorine ion atom. Ionic polarization exists only for this type of materials which have a net positive charge and net negative charge. Even in the absence of an applied field, the HCl hydrochloride molecule has a permanent dipole moment, and that permanent dipole moment can be read as E into D. E is nothing but the charge of the electron, and D is the distance of separation of the ions. In an electric field, the resultant torque lines of the dipoles parallel to the field at absolute zero of temperature. As you can see here in this figure, the chloride and hydrogen showing with the distance d. So the dipole moment is nothing but E into E is nothing but the charge, electron charge into d. This is for per unit volume, E into d. The field produces force on the two charges, positive or negative, as well as a torque on the dipole. The distance between ions increases from d to dx, d plus x. As you can see here, this figure part is of without electric field. Suppose that the electric field is applied, which is shown here in the second figure. Electric field is applied here, then uh, and the ion, one of the ion is displaced from its original position, and it becomes, earlier it is having a distance d, and after displacement it is become a d plus x. Then the field has induced an additional dipole moment, and that dipole moment can be calculated as induced dipole moment pind is equal to E into x. This portion is having additional dipole moment, this portion, it is nothing but E into x. The induced dipole moment is proportional to the applied electric field. It is proportional to the applied electric field, and the proportionality constant is the ionic polarizability. And we have induced dipole moment is nothing but, here you can see pind, induced dipole moment, is equal to alpha I into E. Alpha I is nothing but the ionic polarization. This polarization is also called the molecular polarization, in which the bonds between the atoms are stretched by applied electric field when the lattice ions are charged. The simultaneous occurrence of electronic and ionic polarization results in a volume polarization, which is the sum of individual effect, such that here shown the P is equal to Pi plus Pe, which becomes N into alpha E plus alpha I into E. The distribution of electrons in both the atoms and molecules is almost completely independent of temperature. So both electronic and ionic polarization are independent of temperature. Next is orientational polarization. Ionic bonds are discussed under ionic polarization. There are still other types of atoms which give the at least partly ionic bond. Say A and B are atoms and join to form a chemical bond. Atom A and atom B both are interested to join or form the chemical bond. The existence of permanent movement is purely a matter of molecular geometry. Two hypothetical cases are shown in this figure as a figure A, as a figure A, and as a figure B. These are considered two different hypothetical cases. The molecules are of form ABA. Here ABA. Atom B is negatively charged. Atom B is negatively charged, where atoms A is both positively charged. Here and here also. The arrangement of these atoms is shown in the figure A, which gives net zero dipole moment in the absence of electric field. In the absence of electric field. Whereas the molecular geometry of figure B here gives molecular geometry of figure B gives the resultant dipole moment in the absence of the field. Here you can see this gives the resultant, this is the for positive charge, this one also positive charge, and for the negative charge combinedly it is gives the resultant, means in the absence of it, case B is giving the resultant dipole moment in the absence of the field. CO2 is an, means carbon dioxide is an example of first case, and nitrogen H2O are example of second case. The permanent dipole moment has been denoted as PP, and the presence of an electric field will tend to align PP along its two direction. Since capital E means electric field exerts a torque on PP, the contribution of this process of the orientation of an permanent dipole in the direction of field contributions additionally to total polarization, and it is called as the orientational polarization and denoted by PO. The molecular dipole moments, some materials like CO2, H2O, CH3, CHO are 0.1, 1.87 and 2.72 dBi respectively. I would like to clear that 1 dBi is nothing but 3.33 into 10 raised to minus 30 coulometer. Calculation of the orientational polarization is bit more complicated, and it does depend on the temperature also. While calculation, first step in the derivation of orientational polarization is the calculation of potential energy of a dipole in a uniform electric field. Here, this figure shows a permanent dipole moment, permanent which is showing with the PP dipole moment, permanent dipole moment is showing with the PP, which is nothing but PP is equals to Q into D. PP is equal to Q into D. Q is the charge and D is nothing but the distance between the charges. Q is the total charge. So when an electric field is applied in x-axis, as here showing in the x-axis, then it will produce a force on the positive charge. It will produce a force on the positive charge. That is nothing but F is equals to Q into E. And an equal force at the negative charge also appears. That is F is equals to Q into E. But it is of opposite direction. But it is of opposite direction. Two forces constitute a couple of magnitude. That is nothing but Q into E into D. Q into E into D into sine theta. And it is nothing but it is for a instantaneous value. So to get the total energy required for this dipole can be calculated as omega w of theta is equals to integration from 90 degree to theta q into e into d sine of theta d theta. We will get that finally minus pp e into cos theta and minus pp into e, where the e shows a vector, it is a vector part, and the graphical representation w of theta energy is showing here. It is quite sinusoidal. These are the types of and polarization as well as their details. Thank you for listening to me. Thank you very much.